Greetings to you, channel companions. We are at your service in continuing the robotics education, and in the continuation of the previous chapter, which was the control of motor speed, we want to follow this chapter and introduce you to a new chapter called PWM. In fact, in this session of robotics education, and from this session to the next few sessions, we will discuss pulse signals or PWM so that you know what PWM is and why and how. We can use pulse signals to control motor speed in robotics. First of all, let's see what PWM is. The word PWM stands for pulse width modulation, which gradually. You will understand the reason for this naming well and in a vague way. But it is better to know that PWM is actually a type of signal that can be created by various types of microcontroller ICs or various ICs. Like ICs that actually generate pulses, because in the market we have ICs that generate pulses, which are also widely used in power switching, which are also called timer ICs, such as the 555 IC or other similar ICs. PWM signals are a series of pulses that are generated in the form of a related wave. In other words, the wave is high or low at any given time. Depending on the consumer circuit, you can generate this type of signal for different voltages such as 3 volts, 5 volts, or 12 volts. For example, if we want to consider 5 volts, which is the standard working voltage of most microcontrollers and small motors, at a certain time, it is in the higher 5 volt state, meaning a logic state in this state, and at a certain time, it is low and 0 volts, which is called logical zero. And in this way, zeros and ones are created, which becomes 0 here and 1 here. And you can see the waveform here, which is the same voltage of 5 volts. And here is the same voltage trip voltage. With this image, you can have a first look at the PWM signal. Now consider that this signal is passed in the same way as it passes, for example, to a motor. Well, the motor actually uses 50% of the time. For example, I'm saying you'll learn these percentages well now. If we want to consider time as 1 second, 5% of this 1 second, which can be 5 milliseconds, is in the off state and 5% is in the on state without indicating. So what does this mean? It means that the motor is turning, for example, at 50% of its own speed. If a 12-volt motor is applied, and we have applied this PWM signal to 12 volts, the voltage that reaches the motor is 6 volts. So in this case, the motor is actually turning at 6 volts and is actually using half of its power. And if we increase the percentage of these on and off times, the motor speed will increase because in fact we have given the motor more time when the voltage is 1 than when it is 0. Now, perhaps the first question that comes to your mind is why don't we give the voltage directly to a motor and control the motor speed by increasing and decreasing the current and voltage? For example, why don't we do this? The answer is that when you want to control the motor speed by increasing and decreasing the voltage, in other words, making the voltage and current weak and strong, it is possible manually. But it is not a standard method, and in addition, from now on we will be dealing with digital circuits and microcontrollers. And digital circuits that are programmed work with PWM pulses, and in this way they can control the voltage applied to the consumer and transistors too. Based on PWM pulses, they work much better, and that's why we need to control the speed of the motors using the PWM method. For example, you can't actually define a state for the IC to boost the voltage, so how should you do this? The IC method is PWM, and it comes with the PWM method. It controls the meter and can control the voltage. It can also be said that pulse width modulation, or PWM, is a digital method that can provide precise and accurate control over analog devices. Now that we understand what PWM is, let's see how it works and learn how it works, which will help you understand the PWM controller better so that you can program it when programming the motor control system. For robotics, you can work professionally and act professionally. In fact, PWM provides voltage to the consumer based on time. What does this mean? For example, it takes 50 milliseconds to make the voltage 1 and 50 milliseconds to make it 0. And this waveform looks like this. Here you can see an animation of it. And in fact, this movement is also the pulse of the PW. Now, however much, our pulse generator, which can be any type of IC, should be in the timeline to increase the duration of the one-on-ones. And for example, this time, let's say 700 milliseconds is 1, and 300 milliseconds is just that, meaning the voltage level provided to the consumer has increased. And as a result, the consumer works with more speed and power. And here our consumer, who will be distracted, will be faster. Now, on the contrary, if the duration of the zeros in this timeline is longer, and for example, this time there are 700 milliseconds of 0 and 300 milliseconds of 1, then naturally the speed of the car will also decrease. And in this way, a microcontroller, it can easily control a motor like a stepper motor, both in terms of direction and in fact the speed, which we control with the PWM discussion. The advantage of using PWM with microcontrollers is that based on various parameters, we can program the PWM pulse signal to change its state, and for example, the robot moves at a speed of. And when it approaches an obstacle, it reduces its face, which is the simplest example. For example, a robot moves quickly and at the same time reduces its face or increases its face again. All such functions and control over the motor are possible with PWM pulses. Let's work on all these things that I am saying well and practically, and we will physically build and align the robots. And based on all the things that I am saying here, you can easily see those outputs, meaning in the next session we will have a lot of practical work. First, we will come to the prototype and the circuits. We will also do the test. We will also close the circuit that generates the double PW. We will get the output from it. And later in the next sessions, we will come to what we will do. We will build robots and control the motor using the double PW. And in this way, you will learn practically and truly. And completely and become more skilled. But first, you need to know these things so that when you actually build the robot, you can understand what we are doing. If you, for example, understand these daring things that I am explaining here well, and do not know, and do not say, well, naturally when we come to implement a motor based on the double PW, you may not understand what happened. So be sure to remember these things, and do them carefully, and practice well, and have more studies. So, as was said, a PWM signal stays on for a certain time, and will be off for the rest of the time. If we put all the signals in the one state, that is, there is no time for 0, then it can be said that the PW pulse remains in that state for that time and is in the 100% duty cycle of its own. So if this independence is applied to one motor in the same way, the other motor starts rotating with its maximum power. And for example, if the robot moves with this motor, it moves forward with its last face. Also, the PWM duty cycle is called duty cycle. So wherever you hear the term duty cycle, it means the same PWM duty cycle, and in fact the same PWM. Well, now here I am implementing and performing a PWM pulse generation circuit using the POSDAD, PAGA, and PONJ ICs, and I will also provide the necessary explanations to you. And I will give the explanations on the circuit so that you can see its operation well, and we will use the Parrot software to implement the circuit. And after we have closed the circuit in Protos and implemented a few circuits together, we will implement these in a physical and practical way in the future so that you can get acquainted. So let's see how we can create a pulse generator circuit for the PWM on our Protos. And as mentioned, at first we will use the 555 ICs, which is a cheap and forgiving IC that can be found anywhere you can find this IC. So friends, here as mentioned, we will implement our circuit on the Protos and explain to you how the PWM works so that you can see it in action with your own eyes. Just so that when the video is not taken, I have already drawn the circuit here and actually achieved it, and I am just explaining it to you so that you can operate it well. And in addition, I have also placed the original file of this circuit in the video description section below, which you can easily download, and you can even refer to our website. From the link I posted below, go back to the website and watch the same course and download these files. So we have provided the files to you. In addition, we will also put these files on our Telegram channel so that you have access to these files in every way and don't worry about it. Well, first of all, the issue that I have to say before starting this session, which I have already said before, is that you must know Protos because in this course, our focus is solely on robotics. They will not teach you ProTOS anymore. And of course, we publish the ProTOS training course on the same channel. And you can even learn it elsewhere, but you are publishing a more complete course, so you have to learn ProTOS virtually. When I open the software, I came here like this. As you can see, I have put the 555 IC. I inserted the MOSFET transistor, which you can now choose any type of transistor to make the circuit. I put a motor, and the resistor can be said to be 3, 4, and 5. We have 5 main elements to make the PWM circuit 55 and 5. Another issue is that you do exactly the same thing when you implement the prototype and exit it. That is, we simulate it, which we will do. You can also implement it physically, and it will do exactly the same thing for you. As you can see, I put the 555 timer here, and you probably know that pin 8 of the 555 timer is connected to positive voltage. Pin 1 is negative. So, what did I do here? I came here exactly according to the instructions. You should work. I made the connections. I connected pin 5 using a capacitor. I connected the terminal of this ceramic capacitor, which you can also see here, to ground, pin 2, and the eye together. And he connected the 7th base to the 6th base. With one position, you can put about 3.5 kilos in total. Now you can put 3 kilos in total. Pin 3 of the microcontroller IC is always an output. As you can see, this output goes to the MOSFET gate pin. And from here, I also gave an output to a virtual oscilloscope so that we can observe the wave. So that means pin 3 becomes the output. And then from the positive circuit, that is from the positive voltage, I put a position again, which is 7 kilometers, and I came from the voltage in the real door. I took the base. I connected it to a pin that looks like a 7 ohm resistor. Notice that the pin is like a resistor, and it also has a resistor of about 7 ohms on its end. And you see that the circuit is simple. I also assumed the operating voltage of our circuit to be 12 volts here. Because the 555 IC can easily work with 12 volts. The only problem is that when you close the circuit like this and then want to get output from it, you actually have to simulate it. You might run into an error. Well, this error in ProTOS is because, in fact, women in ProTOS, when the 555 ICs want to work, they are placed in the standard supercharge mode. And in fact, you could say it is an isolated environment. We have to take these capacitors out of the standard mode and into an environment mode. To make it non-isolated means to make it as if the object is in a real environment so that it does not have this error, and we can give this state to the object. Along with the file I provided for you, I placed a text file inside the file folder called Fixerverse. Double-click on it, and there is a code inside. You copy this code, you copy it like this. And when you copy it, it comes up here. You double-click on the object or right-click and click Edit Properties. And you will enter the same code that you copied in this section, that is, in the Other Properties section. As you can see, I entered that code before. You post it and click OK. Do this. You won't get any more errors during the simulation. So now I'll tell you what we're going to do. We're going to do the simulation. I'm going to click this button. You can see that our circuit has started to simulate. And here you can see the motor slowly turning. You can see the pulses. If I zoom in a little bit, you can see that the pulse that is currently reaching the motor is generating VCPN 75 and 55 and giving it to the MOSFET transistor, which in turn controls the motor. So you can see it here. As mentioned before, this is part of wave 1. And do you see this part of the journey? One trip, and since we put the pulses on the pedal, the motor it works at half its power, and if we increase the pulse and increase the number of ones, this motor will spin at high speed. Well, now you might be wondering how we can implement a circuit using a 5-to-5 IC that actually generates pulses for us. For example, how do we know what they want us to put here, what position to give it, what to do? For this, although learning calculations itself is very helpful, in order to somehow get ahead and get started, first use the tools to quickly take advantage of the calculation opportunity. Have fun and learn. I will introduce you to a very, very important and useful software that is specific to the IC 555, which allows you to actually design the circuits that generate the PW pulses. And I have included this software along with this tutorial. The link is at the bottom of the video description section, which you can easily follow, and it is also open on the Telegram channel. The name of the software is Punzd and Ponge Pro, which I will click here to run, and you will see how it works. So when you open the software, it looks like this. It is a very simple software, Ponson 5 and 5-timer design. The original name of the software. Well, a software is no longer easily found, and it was at our disposal, which we also present to you dear ones. Now, what does the software do? It comes here, and when you click on the design section, you will see for Windows, one of which is stable, and in fact all of them are written stable, and one is monostable. What is there here? Pay attention to the text iodo cycle has a big small sign. 5%. What does this mean? It means that if we want to design a circuit that its DOT cycle wave is greater than 5%, that is 5% and above, then we should use it here. If we want to produce a DOT cycle that, if the wave is equal to 50%, it actually gives 50% of the pulse. Now you have learned this discussion of 50%. Then we will consider a period of time, for example, a second, well. And half of this 1 second, which is a fifth of a millisecond, is 50%. That is, if, for example, we want to rotate a 12-volt motor at half its speed and power. We can use this section, and this circuit will give us a pulse of 50%. If we want the fifth percent to be greater, which means that the motor speed is actually higher and the duty cycle is greater than 50%, then we will choose this circuit. And if we also want it to be in a stable state, then we will choose the monostable. Now what do I do here? If I want the speed of the meter to be low, with a lower speed, well, you can understand it from its sign. The number of 1 hash is smaller, and the number of bile is larger. So that means the daemon in my cycle is smaller than 5%, so I can choose this. But if I want to choose more than 50%, then my cycle is larger and 1 hash is larger. I can choose this. Now I'm going to click on this section, for example, right at the beginning, and you'll see that it's telling me the circuit, but this circuit hasn't specified a number for me yet, right? For example, I'm mixing with a frequency of, say, 150 hertz and my duty cycle is, say, 70%. And I click on the calculator. Now this time it will add up the number of your rank and the number of your relatives, and my justified type will be like this. Now you can implement exactly the same thing on the Pertus, and if you look closely, the circuit is almost the same, just the resistors. Their meanings are different. Now I'm going to change the meanings of your positions and such, and the circuit will actually be a little different. Then I'll do the test. What do I do now? First, I'll download these files. I'll clean it up. First, let me put the circuit here, meaning I'll remove the resistors. From here, I'll just put the transistor and the MOSFET, meaning the one with the motor. Okay, the first thing we do is connect pin 3, which is supposed to be the output of our IC, to the actual gate pin of the MOSFET. Here we connect this MOSFET pin to the GND. So, we set our voltage to 12 volts and connect the 8th pin of the IC to the 12 volts and give a positive to the motor. This is what we're going to do now. For plus 5 and 5 always add up to 8, just like we're saying here, which means it's a positive number. Then according to what is said here, we connect the 2 with the 6, so we do this, and then we connect the 2 with a 100 nanofarad capacitor to ground. And here we replace the capacitor. I put it here before, and we'll connect one side to the ground. And we right-click, and we do this. When was it that we were asked to convert 100 nanofarads? We right-click in the edit section, and here we convert 1 nanofarad to 100 nanofarads. And the code that I told you, you must copy that code, then come here in the adder properties, paste it like this, and click OK. That's no problem anymore. We don't have a simulation either. So what should we do now? We'll connect a resistor from the positive to pin 7. We'll put a resistor like this here. We'll take a voltage from the positive and connect this in to pin 7. And its ohms are about 11.5 and 4 kilos. We'll right-click and come here. We'll enter 11.5 and 4. So this is from this, and then again from this 7. We'll put another position. We'll right-click. We'll hit the root to rotate. Again, we'll take it from pin 7, this resistor, and this resistor comes directly to pin 2, which actually becomes 1 with a base of 6, as if it is connected to 2. You see it is connected to 2. And well, on the other hand, if they want, it is actually connected to the ground, but we also put this position, that is 8 kilowatts. 8 museum 658. 0.6705 and 6 kilowatts. That is this from here, and we connect the base of 5 to the ground with a 10 nanofarad capacitor. That is, we put the 10 nanofarad capacitor here. You want to connect the fifth to it, and on the other side that connects to the Jindy, this is also 10 nanofarads. Be sure to leave this code for the girls. We will also do this 10 nanofarads and okay, well, this from this, and I think there is no problem. Now we will run a circuit from it to see how it is. Philanthropy, we will minimize this, and I expect that our motor will cycle at a faster speed. Let's start our oscilloscope. Well, the motor that you see is starting up with more phases. Here, I had a small mistake that I forgot. You see our motor starting up. I'm going to use 3. I also need to get a probe, connect it to my stylus, and then my stylus can show it. And then I'll do the simulation again, which means that the 70% pulse that we selected is actually reaching this motor. So, if you have some problems in Protoss, for example, that the oscilloscope doesn't come up, you want to delete this object and go back to this section. And from here, select the stylus and place it because sometimes Protoss has a bug that, for example, doesn't show the stylus even though it's active. It does its job, and we see that our stylus came up. This was also a kind of trick. Now get to know the Protoss bugs. So you can see that it's showing us the wave. You can see that I'm zooming out. You can see that the time interval between zeros is much less than 1. You see that the ones are much larger. Their time interval is actually this length of the timeline, and the zeros are shorter, and this is what makes the engine run faster. You see it's very easy. Now what's interesting? The main thing is that the pulses change with changes in resistors and capacitors and things like that. That is, you don't have to change the circuit every time. You just need to set these values in the capacitors. For example, I'm going to put this capacitor. This time I'm going to put 100 nanofarads, right? And for example, I'm going to change this value from 11 kilos to about 10 kilos. And then I'm going to output the result again, and you see that. The wavelength has changed again, and the zeros have increased a little bit, and the ones have decreased. And the motor speed has also decreased a little bit. And just like that, you can actually change the output and the type of pulse very easily. When you do this and get your circuit output like this, you'll be sure that it's working properly. What can you do? You can do it very easily. Let's actually implement this circuit physically. That is, make a slave motor. You can even make a PCB for this and use it in the real world. Very easy. This will be possible, and you have seen how we can actually control the speed of the motor using PWM. Now we go to this soft control, and this time we want to tell it that instead of, for example, we want to control the speed of the motor in percent. Everything is the same, only that changes. You see that it changed here. Okay, this capacitor is also 100 nanofarads. This one is 10 nanofarads. Now we're going to apply the changes. We will again make 5 10 nanofarads. That is, the one that is connected to the 5th pin, and then this one that is 100 nanofarads. We will make this one about 2 kilos, 2.35 and 35. About the voltage of the positive terminal, 23 kilos. This is 10 kilometers here. I'll do it 23 riddles 3, 23 riddles 3, and then this one will also be 2 kilometers. This was 8 kilometers. 2 riddles 335, because 90% more now. What do I expect? The motor is much quieter. So this is also one of the changes we have made. Now we will do the simulation again. You can see how many times it has increased, and the motor has naturally become faster. As you can see, so here as you can see the trip, and the duration of the trip has become very short and one is very long. In this way, you can easily make the picture circuit using IC 5 and 5 and 5, and this IC, in fact, you can also connect it to a microcontroller using a microcontroller. Come on, let's control this. For example, now, if we come to control the amount of voltage that reaches 2, we can actually pulse. Without even changing the resistors and capacitors, let's change the value of the picture. For example, how do I come here instead of this resistor? Well, instead of this, I'll put this here and replace it. I'll put a potentiometer like this. I'll connect one side to the same pin 6, the other side to your pin 7 here, and the other side to the pin 6 again. Let's see what output we can get from it. When we do the simulation, you'll see that the mooches are now glued and they work with almost 100% power. That is, without us wanting to change the positions, we can only change them with the potentiometer. Now your potentiometer increases. You pay attention to the pulses on the oscilloscope here. I'll put it here and turn on the motor. You'll see that I'm not decreasing it. In fact, this time delay and zeros are increasing. If I move the bar up, you can see that the motor speed increases, and now we have a smooth DC wave. Here, the screen is completely gone. Now if we come to here, for example, this potentiometer means that from now on, you can control the motor speed by turning a potentiometer using the PONGSAT and 5 ICs. We will do the simulation again, and you can check the result again. So, we can make the necessary changes to our circuit just by placing the potentiometer. Now, instead of the potentiometer, we can put a microcontroller and let that microcontroller give different pulses to the 55 and 55 ICs. Let's see, when I turn the potentiometer, as you can see, the distance between the screens becomes a little wider and the motor rotates with less force. If I want to zoom in, it has a similar state now. In fact, our PWM is delivering a voltage to the motor in this way. So you can see that you can easily design an oscillator circuit to control the motor using ICs 55 and 55. And it is very, very easy. There is also a good thing in this that I have introduced a very good software that will help you in this matter and use it properly. It is very easy. You enter the pars here, and this is the big discussion that was presented and also a percentage of the soccer DeVito here, and the software will give you the map, and you can easily implement this map here. This is also from the PWM discussion of this session, and it is true that the videos are long, but it is completely worth it for you to watch these bit by bit and review them several times until you get it completely. I suggest that you test the session that you have seen so far, maybe dozens of different circuit models. Be sure to test it on Paratas, get the output from it all, and practice well. That is, make dozens of circuits, dozens of Parsa and PWB circuits, even your own creations. Use your creativity and don't worry. The best thing is that the circuit doesn't work, but you don't get anything. If an idea comes to your mind, do everything and follow the standard method. These are the ones I taught you so far. And in this way, you can easily make your own PWM circuits to control the odometer. This circuit is not necessarily for robotics either. For example, you might want to control the speed of a motor using a potentiometer, right? Now, not just for robots, for any other use, this will allow you to do it very easily, and you can use it. This is also the discussion of PWMs in the next session, and from the next session, we will enter the physical phase. Of course, in the next session, I want to introduce the discussion of microcontrollers and implement a circuit based on a microcontroller, for example. Here, in fact, we can get an output from it and observe the PWM generated by the microcontroller ICs, which is done with programming. And you learn them too. From the worst session, that is 3 or 4 worst sessions, we will move on to physically implementing the same routine that you worked on here. Well, friends, I hope it was useful for you. And this was from the 7th session of robotics. You can see the links to the past sessions at the bottom of the video description section. You can download these files both on the Telegram channel, and I have put the link below. You can download and receive them, both the software and this file, and use them. I hope that the session was useful for you. And until the next session, when we will gradually become more robotic, God bless you.